The activities presented in this talk are part of the PRIN 2022 project 6GTWIN. The project is founded within the Italian National Recovery and Resiliency Plan, supported by the PNRR and the European Union. Within this context, the work of the Rome Research Unit focuses on the use of digital twins to support the coordinated decision-making in next-generation network infrastructures. The title of this presentation is Coordinating Network Decisions with Digital Twins, the 6GTWIN Approach. I'm Marco Polverini from Sapienza University of Rome. Today's communication networks are evolving toward highly programmable and automated infrastructures. The vision of future 6G networks is strongly based on softwarization, where network function, control logic, and services are implemented as a software components rather than dedicated hardware. At the same time, network infrastructures are becoming increasingly distributed. Computing resources are spread across cloud and edge environments, and services may be dynamically instantiated across geographically distributed platforms. This evolution enables unprecedented flexibility, but it also increases system complexity. Network management and control are progressively relying on automation and AI-driven mechanisms to operate efficiently at large scale. As a consequence, network control is no longer centralized in a single entity. Instead, decisions are increasingly taken by multiple components operating at different layers of the infrastructure. And this raises an important question. How can we coordinate this distributed decision process? Two key paradigms have played a fundamental role in enabling the softwarization of communication networks: software-defined networking, or SDN, and network function virtualization, or NFV. Software-defined networking introduces a separation between the control plane and the data plane. This allows the control logic of the network to be implemented in software and executed by programmable controllers, enabling flexibility and dynamic management of network behavior. Network function virtualization focuses instead on the virtualization of network functions. Traditional network appliances, such as firewalls, gateways, or load balancers, can be implemented as a software components and developed on general-purpose computing infrastructures. Together, SDN and NFV provide the technological foundation for building flexible and programmable network infrastructures. These paradigms are widely recognized as key enablers of the next-generation communication system, including 5G and emerging 6G architectures. While SDN and NFV enable flexibility and programmability, they also change the way network control is organized. In modern networks, control logic is no longer concentrated in a single entity. Instead, it is typically split across multiple components. There are several reasons for this architectural choice. First, scalability. Large-scale infrastructures cannot be efficiently managed by a single centralized control logic, so responsibilities are often decomposed across different components. Second, administrative and domain independence. Different parts of the infrastructure may belong to different operators or administrative domains, each with its own control policies. Finally, network control itself is becoming increasingly modular, with specialized components responsible for different management functions. Because of these factors, modern network infrastructures increasingly behave as agentic systems, where multiple decision-making entities operate simultaneously and interact with each other. Each of these entities typically has only a partial view of the system, and decisions taken by one component may influence the behavior observed by others. This leads to an important challenge. How can we coordinate network decisions in such environments? This is the problem that motivates the use of digital twins as a support mechanism for decision-making and coordination. Before discussing the coordination problem in more detail, it is useful to briefly look at how decision processes are structured in the two paradigms we introduced earlier, SDN and NFV. In software-defined networking, control is logically centralized through the SDN controller. However, the controller typically hosts multiple SDN applications, each implementing a specific network policy or optimization objective. These applications collectively determine the behavior of the network. In network function virtualization, decision-making follows a different structure. Service deployment decisions involve hierarchical management architecture, where components such as the orchestrator and the infrastructure managers cooperate to allocate resources and instantiate network services. Although in these two paradigms the control is organized differently, they share a common aspect. Network behavior results from the interaction of multiple software components, contributing to the overall decision process. This observation brings us to the key issue we address in this work. How can we coordinate these decisions effectively? We can now make the coordination problem more explicit. In modern network environments, multiple decision-making entities operate simultaneously, each with its own objectives and only a partial view of the system. Because of this, decisions are not independent. The effect of a decision taken by one component might depend on the decision taken by others. Different paradigms organize this interaction in different ways. In some cases, such as in the NFV environments, decisions follow a hierarchical structure, where a central entity coordinates lower-level components. This is what we refer to as master-slave model. In other cases, such as in multiple application SDN environments, decision-making entities operate at the same level and interact with each other without a strict hierarchy. This corresponds to a peer model. Although these models are different, they share a common challenge. How can we ensure that individual decisions lead to a coherent and efficient global behavior? Addressing this challenge requires mechanisms to evaluate the impact of decisions and to align them across different components. This is exactly where digital twin can play a key role. To address the coordination problem, we adopt a different perspective on how decisions are taken. In many systems, decisions are still made using a trial and error approach. A change is applied and its effects are observed afterward. This approach may work in simple scenarios, but it becomes increasingly problematic as systems grow in complexity and multiple decision-making entities interact. Digital twins provide a different approach. At a high level, a digital twin can be seen as a representation of a system that supports decision-making, allowing us to interact with the system before actually acting on it. This introduces a separation between deciding and executing, which is particularly important in complex environments. Instead of applying a decision directly, we can first reason about its potential effects. This leads to the key capability enabled by digital twin, which is what-if reasonings. Rather than modifying the real system and observing the outcome, we can explore alternative decisions, anticipate their consequences, and make more informed choices. Building on this idea, we can interpret what-if analysis as a form of coordination API. Instead of directly interacting with the system or with each other, decision-making entities can query the digital twin by submitting candidate decisions and observing their expected outcomes. In this view, the digital twin acts as an interface between decision-making components and the system, providing feedback on the potential effect of their actions. A key property of this approach is that the interaction can be treated as a black box. Each entity does not need to know how the digital twin internally evaluates decisions, nor does it need to fully visibility of the system state. This is particularly important in scenarios where components belong to different administrative domains or implement proprietary control logic. By avoiding the need to disclose internal information, this approach naturally supports administrative independence. At the same time, the use of a standardized query interface enables scalable coordination, since each entity can independently evaluate its decisions without requiring tight coupling with others. In this sense, what-if analysis provides a simple but powerful mechanism to align decisions across multiple actors while preserving autonomy and abstraction. Let us now focus on how this concept applies to the SDN environments. In practice, SDN controllers typically host multiple applications, each implementing a specific control objective, such as routing, security, or resource optimization. These applications operate on the same infrastructure, but they are often developed independently and without explicit coordination. As a result, their decisions may interact in non-trivial ways. In particular, actions that are locally correct for a given application may lead to unintended effects when combined with decisions taken by others. These interactions are often difficult to anticipate, since applications have only limited awareness of each other's behavior and objectives. This may result in policy violations, performance degradation, or inefficient use of network resources. This motivates the need for mechanisms that allow us to anticipate the impact of control decisions before they are enforced. Let's now look at how the proposed approach is integrated into an SDN environment. We start from a standard SDN architecture composed of the network infrastructure, the controller, and a set of applications implementing different control functions. On top of this architecture, we introduce a set of additional components to support what-if analysis. The first component is the Digital Twin Manager, which acts as the orchestrator of the analysis process. It is responsible for receiving candidate actions and coordinating their evaluation. The second component is the Digital Twin Wrapper, which provides a standard interface between applications and the what-if framework. Through this interface, applications can interact with the system in a uniform way. Finally, we consider a set of digital twin models, each focusing on a specific aspect of the system behavior. Overall, this results in a modular and extensible architecture, where new models and new functionalities can be integrated without modifying the core SDN components. Let's now briefly describe how a digital twin analysis is performed. The process starts when an application proposes a control action, such as a routing decision. This action is immediately executed in the network, ensuring that the system remains responsive. At the same time, a what-if analysis is triggered in parallel. The framework collects the relevant information about the current system state and the application context, and selects the appropriate digital twin model for the evaluation. The model is then used to estimate the impact of the action, for example in terms of performance, resource usage, or policy compliance. Once the analysis is completed, feedback is returned to the application. This allows the application to take the result into account and potentially adapt its future decisions. Let's now briefly discuss a proof of concept to validate the proposed approach. We implemented the framework in a mininet environment, integrating it into the POX controller. In this setup, we consider two types of traffic: multimedia flows with strict bandwidth requirement and best effort traffic, sharing the same network resources. As shown in the figure, we can observe the evolution of the throughput over time for different flows. At a certain point, multiple flows start sharing the same link, and available capacity becomes insufficient to sustain the required performance. As indicated by the dashed red vertical line in the figure, this is the moment where the digital twin flags a potential conflict. By performing what-if analysis, the framework is able to detect in advance that the current decision may lead to violation of a multimedia flow requirements. In our experiments, these situations are correctly identified as congestion builds up. An important aspect is the execution time. The analysis completes in less than 15 milliseconds, which makes the approach suitable for real-time decision support. Let's now consider the NFV case, where decision-making follows a hierarchical structure. In this setting, service deployment is decomposed across multiple layers. The orchestrator takes high-level decisions, while lower-level components are responsible for allocating resources and enforcing them within the infrastructure. This decomposition is essential to ensure scalability and administrative independence across domains. However, it also introduces a fundamental limitation. The orchestrator does not have full visibility of the system. It can only rely on abstracted information about the available resources, without access to how those resources are actually managed at the infrastructure level. As a result, decisions are taken based on a partial and aggregated information. This may lead to situations where a decision that appears optimal at the orchestration level turns out to be suboptimal once applied to the actual infrastructure. In other words, there can be a mismatch between the global objective and the actual system behavior. This is what we refer to as the hidden state problem. Let us now look at how the proposed approach is integrated into the NFV orchestration framework. The key idea is to associate a digital twin with each infrastructure domain, that is, with each NFVI point of presence. Each digital twin is managed locally by a component called the Digital Twin Management Agent, which is responsible for maintaining an update view of the infrastructure and exposing a what-if interface. At the orchestration level, we introduce a lightweight component referred to as what-if execution agent, which interacts with multiple domains. When the orchestrator needs to evaluate a candidate service deployment, it does not directly rely on abstracted information. Instead, it queries the digital twin associated with the different POPs. Each digital twin evaluates the candidate allocation based on its local view of the system and returns an estimate of its impact. These estimates are then aggregated at the orchestration level, allowing the orchestrator to compare different alternatives before making a decision. In this way, we obtain a clear separation between prediction and decision making. Predictions are performed in a distributed manner, close to the infrastructure, while decisions remain centralized at the orchestrator. This enables more informed orchestration without requiring direct access to the internal state of each domain. Let us now briefly discuss the proof of concept developed for NFV scenario. The goal of this implementation is twofold. On one hand, it validates the integration of the proposed digital twin-aided orchestration framework within the MANO architecture. On the other hand, it enables the generation of realistic data to support the training of the digital twin models. As shown in the figure, the system is deployed on a physical testbed composed of two main subsystems. The first one provides MANO functionalities and is based on an open-source MANO deployment. The second subsystem represents the NFVI infrastructure implemented as a Kubernetes cluster distributed across multiple servers. This setup allows us to emulate a realistic orchestration environment where network services are instantiated and executed over time. Service requests are generated dynamically, creating evolving workload conditions. At the same time, the infrastructure state is continuously monitored. This information is collected and used to build a dataset that captures the temporal evolution of the system. This dataset is then used to support the digital twin models, ensuring consistency between training and runtime behavior. Overall, this proof of concept demonstrates both the feasibility of the architecture and its applicability in realistic NFV environments. Let us now look at some results obtained with the proposed approach. On the left, we show the accuracy of the digital twin model. As we can see, the predicted cost closely follows the actual cost, with most points lying near the diagonal. This indicates that the digital twin is able to provide reliable estimates of the impact of a candidate allocation decision. On the right, we show the system-level impact of using these predictions in the orchestration process. In particular, we compare the cumulative cost over time for different strategies. As we can see, the DT-aided approach achieves consistently better performance compared to baseline strategies. This highlights an important point. Accurate predictions are not only a modeling result, but they directly translate into improved decision-making at the orchestration level. Let me conclude by summarizing the main contributions of the Rome Research Unit within the 6GTWINS project. The starting point of our work is the observation that modern network infrastructures can be interpreted as agentic systems, where multiple decision-making entities interact with each other. In this context, the key challenge is not only to make decisions, but to coordinate them effectively. To address this problem, we proposed a methodology based on digital twins, used as decision support tools. In particular, we introduced the idea of what-if analysis as a coordination interface, enabling different components to evaluate and align their decisions without requiring direct coupling of full visibility of the system. We then demonstrated how this approach can be applied to different network paradigms. In SDN, it supports coordination among peer decision entities, while in NFV it enables the decision-making under partial observability. Overall, our contribution moves toward a unified framework for coordinated decision-making in next-generation networks.